This is the third video and last video in the Fourier Series section of the course. I just want to tell you about a few subtleties of Fourier Series that you should be aware of. We'll continue talking about our example function that we've been doing, a step function. So I've plotted it here on the screen. It is 0 from minus pi to 0 and 1 from 0 to pi. And in the last two videos we showed that this step function can be written as a series over sines and cosines, where in this case only the sine function appears. So before we get too fancy, let's just see what this series looks like. If we include just one term, then we're not going to get much, we're just getting a half. So okay, one term here of the series doesn't approximate this function very well. But if we add another term, now we've added a sine of x term. Now it's starting to look a little better. And if we add three terms, so now we have these three here, you can see it's looking a little closer to the step function. If we include all four of the displayed terms, it looks like that. And we can keep going. 5, 6, 7, 8, 9, 10. Now notice that after 10 terms in the series, it really is looking an awful lot like a step function, at least over here, kind of in the nice area of the function. But in the middle, where there's this discontinuity, it's not doing so well. There's a much bigger error here than here in the middle. And in fact, that's a totally general feature of Fourier series. If there's a discontinuity in the original function, the Fourier series doesn't do very well there. This is called a Gibbs phenomenon. So that's one subtlety to be aware of. But notice that if we evaluated exactly right at the point of discontinuity, at 0 here, the value is 1/2. And I don't know if you noticed, but no matter how many terms I included, it's always 1/2 for this particular function. And in fact, it's a general result that when there is a discontinuity, the Fourier series will converge to half the value, or rather the average value at the jump. So this was 0 from the left and 1 from the right, and the Fourier series likes the value 1/2. So that's sort of how Fourier series works. If you have a few terms, you don't get a very good approximation, but if you add enough, it gets better and better and better. Now 10 terms is actually quite a bit, and you can see we would need many more to really get a good approximation of the step function here. So you might be surprised that it's converging so slowly. Well, that has to do with the fact that there's a discontinuity here. If this were a nicer function that was, say, smooth everywhere, then actually the Fourier series would converge quite rapidly. And there are theorems that govern that. The other thing I want to point out here is notice that there's also some funny business at the edges of the domain. This has to do with the fact that you can really think of Fourier series as approximating periodic functions. Because even though we thought about our original step function as being defined on minus pi to pi, when we write it as a Fourier series up here, we're using sines and cosines, and that is naturally a periodic function with period 2 pi. And so you should really think of the left-hand side as a square wave that kind of goes in a square, as my mouse is indicating. And so what we're seeing here and here is just the discontinuity between minus pi and when it wants to go back up to pi on the other part of the square wave. So if the function you're expanding doesn't have the same value at minus pi as it has at pi, that really counts as a discontinuity. All right, so this example is actually quite illustrative of the general result that we're going to talk about. There are many, many theorems about when Fourier series converge and how they converge, but this is sort of the most common and the most useful, and the one I want you to understand for this course. So it's called a Dirichlet type condition for convergence. You can find it in the book by Boas, and here's what it says. It says you take a function f of x, it's defined on minus pi to pi, and you make sure it satisfies three things. It can oscillate, it can have many maxima and minima, but it has to have a finite number, like 10. It can't be some crazy function like sine x over x, which oscillates infinitely many times near the origin, but is nevertheless continuous. So it has to have a finite number of maximum and minimum values. It can have discontinuities, as we've seen, but it has to have a finite number. It can't do that jump infinitely many times. And you have to be able to compute its integral. This sort of makes sense because the way you get the coefficients in the Fourier series is doing various integrals involving x. So at minimum, its absolute value has to be integrable, has to be such that if you compute this thing, you get some finite answer. So it can't blow up very rapidly, for example, at one of the edges of the domain. Okay, so if you satisfy these three conditions, there are theorems that will guarantee that the Fourier series converges. Now, at a nice value, like minus pi over 2 or whatever, the Fourier series is going to converge to whatever value f takes there, in this case, 0. But at points where f is discontinuous, it's going to converge to the average value, as we mentioned again. So up here, in our simple step function, the average value between 0 and 1 is 1/2, and that's what the Fourier series is going to converge to. And in fact, for this series, it's equal to 1/2 for every partial sum. And as I mentioned earlier, this sort of edge, if it's not equal to itself on the left and on the right, that counts as a jump for the purposes of this theorem, and the Fourier series will converge again to the average value of that jump. And that is all I want you to know about Fourier series.